the flat plate boundary layer, turbulent flow. There is no exact theory for turbulent flat plate flow, although there are many elegant computer solutions of the boundary layer equation using various empirical models for the turbulent eddy viscosity. The most widely accepted result is simply in an integral analysis similar to our study in the previous chapter for laminar flow. We began with the equation of the shear stress on wall for as a function of momentum from the definition of the CF, which is the friction shear wall constant, shear wall coefficient, we can write as this relation. Now, if we consider the figure for the turbulent flow profile as this provided picture, that the turbulent profile are nowhere near parabolic. Going back from previous section for a flat plate flow, it was concluded that the flat plate flow is very nearly logarithmic with a slight outer break and a thin viscous sublayer, therefore just a turbulent pipe flow. We assume that logarithmic law also here, which had a relation for the logarithmic law for pipe flow in previous chapter 6. Where U star viscosity velocity, friction velocity, the parameters K and B equals to 5. At the outer edge of the boundary layer, we had this condition: velocity equals to the upstream velocity. So we can write the equation for the logarithmic equation for this case of study. We have at delta at y equals to delta U star on but the definition of the skin friction coefficient is such that the following identities hold. So we can assume that U star is a function of the friction. We can calculate the U on U star is a function of the friction shear wall, friction coefficient on shear wall, and we had also this relation from calculation. The full calculation of this relation is available in more related and expertise books such as Boundary Layer of Schlichting. Now we can simplify the relation of the logarithm law and replacing with these two parameters, we can obtain a function for friction factor and the Reynolds of the delta. The final relation is plus 5. This is complicated law, but we can list solve for a few values and list them for values Reynolds number. Following a suggestion of Prandtl, we can forget the complex log friction law that is, let me name it log friction law. In the Blasius form, we can have different relations and simplify the numbers in the table to a power law. If we sketch the Reynolds and the delta Prandtl, suppose that the CF is equal to the Reynolds with experiment and calculating values friction coefficient V Reynolds number. This we shall use the left hand side of friction factor equation. For the right hand side we need, so we have CF for right. For the left hand side, the Reynolds number and the friction coefficient was the relation with the momentum one-dimensional parameter, and the right hand side Reynolds number. We need an estimate for delta x and the term of, we have u delta unknown, and we should estimate a theta x from a delta x quantity. In we use the logarithm law as we stated before, we shall be up to our Gibbs logarithmic integration for the momentum thickness. Instead, we follow another suggestion of Prandtl, who pointed out that the turbulent profiles that's provided in previous figure for Blasius equation can be approximated by a 1/7 power law, which is the non-dimensional velocity for turbulence case equals to y on delta. This is shown as a dashed line in the Blasius equation in this picture. The dashed line are the 1/7 law of the velocity profile, and in fact this is the function that shows this dashed line here and here for turbulent, and laminar we can have another expression for turbulent. We have this turbulent relation. This is shown a dashed line in this figure. It is an excellent fit to the low Reynolds number turbulent data. Low Reynolds turbulent data. Which were all that were available to Prandtl at the time. With this simple approximation, the momentum thickness can be easily evaluated as this relation with integration. We can calculate the momentum thickness as a function of the boundary layer displacement thickness, or as another function we accept this result and substitute to the CF as obtained by the Prandtl as this relation to recently calculated momentum thickness. We can write this CF Prandtl equation, which was d2 d theta on dx, in this case 2 d on dx delta, excuse me, or we can write, simplify this relation, we can write Reynolds, this relation Reynolds delta equals to, simplify the relation, d delta on dx. Or can be write as this relation. So we can calculate Reynolds delta Let me write again. We have this relation Reynolds delta, which is the displacement boundary layer thickness, a function of Reynolds x, or we can write delta on x equals to this relation Reynolds x thus the thickness of turbulent boundary layer thickness of the turbulence boundary layer. The thickness of the turbulent boundary layer increases proportional to x 6/7, the root of 6/7, and far more rapidly than the laminar increase with x 1 second flow. These equations is the solution for the problem because all other parameters are now available for combining this equation with the previous obtained friction factor CF can be calculated as we previous obtained CF for turbulent flow delta minus 1/6 with the replacement of Reynolds data. We can have a relation for CF as Reynolds of the Reynolds X CF Writing this out in dimensional form, we can have a relation for shear stress at wall for turbulence flow. We can write this relation. Turbulent plate friction drops slowly with x. So in this case, turbulent drops slowly with x, increase nearly as rho and increase rho and velocity square, and is rather insensitive to viscosity. We can evaluate the drag coefficient also by turbulent flow. With integration of this relation, we can obtain the drag coefficient was integration of forces on the area, which is it is dA. So now we can calculate CD, which is drag coefficient. So we can write 6 CFN. Density, the dry coefficient is only 16% greater than the trailing edge skin friction coefficient. Experimental data, 16% error was reported. The displacement thickness can be estimated from the 1/7 power law also. We have displacement thickness delta star. Delta is boundary layer thickness, delta star is displacement thickness, where we have a parabolic shape of velocity in that thickness. The turbulent flat plate shape factor is approximately turbulent flat plate shape factor. We write turbulent flat plate shape factor delta star on the momentum thickness. Obtained before, we have delta and delta, we can obtain it h equal to 1.3. This figure shows flat plate drag coefficient for both laminar and turbulent flow conditions. The smooth wall relations expressed before, and also the drag coefficient for turbulent flow are shown in this picture, along with the effect of wall roughness. Which is quite strong. The proper roughness parameters here is roughness X on epsilon or L on epsilon. By analogy with the pipe parameters, also for pipe we have D on epsilon, epsilon on D for the pipe. In the fully roof regime, drag coefficient is independent of the Reynolds number, so that the drag varies exactly as velocity upstream velocity square, and is independent of the viscosity. We can write a two relation for fully roof regime for skin friction and drag friction as this equation. For the skin friction, shear related to shear wall, we have and also we have drag coefficient L on epsilon this equation is plotted to right of the dashed line in the picture. Let me provide the picture here. The dashed line separated the laminar and the dashed line. Here, right hand side, we have these areas. Right hand side of the dashed line, excuse me, right hand line, sure, left. Right hand side, the dashed line. The drag coefficient. The figure also shows the behavior of the drag coefficient in transition region, which shows in this picture here, where Reynolds L where the laminar drag at the leading edge is an appreciable fraction of the total drag. Schlichting suggests that the following curve fit or for these transition drag curves depending on Reynolds number and namely Reynolds transition. And we have this coefficient for drag force according to the transition condition. The first is Reynolds L, where the Reynolds transition Reynolds L minus Reynolds transition This is the end of the turbulent flow on a flat plate. Drag coefficient and the boundary layer thickness, displacement thickness and momentum thickness were described and the relation provided. The next chapter is boundary layer with pressure gradient.